Hey there, Gregory Carlson here with the Calculus Building, and we're about to learn a very, very simple but powerful rule that's going to make taking derivatives, it's going to make it really easy. And the question is, say I have a function, f of x, and it's equal to x to some power. Now, the question is, what is the derivative? And it turns out that the derivative, f prime of x, is equal to, so if you have x to some power, you just move the power down in front, and then you just lower the exponent by 1. And that's it. No, really, that's it. And that works for a cubic function, a power of 4 function, 5, 6. It doesn't matter what the power is. And that's just incredible to me. So let's look at the proof just to demonstrate that this is the derivative. Now, this proof I'm going to show you technically only works for natural numbers. And so, but it turns out that this works if n is a real number. N can be any number you want as long as it's a real number, and this proof will work. So let's look at the proof. Again, my function is f of x is equal to x to some power, and we're going to use the definition. So the limit as h goes to 0 of f of x plus h minus f of x all over h. We know that definition by now. So let's plug in our function. So that's going to equal the limit as h goes to 0. And so this is going to be x plus h to the n minus x to the n all over h. So you can see how we've applied this definition onto f of x, and you see we've got x plus h to the n minus x to the n all over h. So now I'm going to do something kind of tricky. I'm going to expand this with the binomial theorem. So if this part's tricky, I might do a supplemental video just on this. But what this would equal is, we start with n choose 0, x to the n, h to the 0. Okay, that would be the first term. The second term would be n choose 1 times x to the n minus 1, h to the 1. Okay, that would be the second term following the binomial theorem. That would go on for a while. Then the last term would be n choose n. And then we would have x to the 0, h to the n. Okay? Don't forget we're subtracting x to the n, and this is all over h. So I know that might be a little bit confusing, but basically what we did there, this first part from here to here is just the expansion of x plus h to the n. Then we take off x to the n, and then that's over h. So let's simplify this a little bit. N choose 0 is just equal to 1 right there. And h to the 0 is just equal to 1. And so you see that I have x to the n minus x to the n, and those would just cancel. Okay? By the way, n choose 1 is just n, so let's rewrite this. The limit as h goes to 0, so it'll be, again, n minus 1, n choose 1 is just n. And then we would have a whole bunch of terms. Oops, I'm sorry, I left off my h to the 1. And then we would have n choose 2, and this would be x to the n minus 2h squared, and so on, all the way to n choose n, x to the 0, h to the n. Okay? So there we are right there, and you can see I've got my nx to the n minus 1. I mean, that's the answer we're hoping to get, so that's good that we can see that in our formula. And so basically what's going to happen is, if I factored out an h, this would not have an h anymore, but everything after that is going to have an h of some power. That's going to have an h of power of 1, the next one would be 2, 3, and that would be h to the n minus 1 after I factor out that h. So that's what I'm going to do now. I'm going to factor out the h, and we're still taking the limit as h goes to 0. So I get n to the x minus 1 plus, this will be n choose 2, x to the n minus 2h, and so on, all the way to n choose n, x to the 0, h to the n minus 1. So the moral of the story is I just factored out an h, and so I can cancel that h right here before I take the limit. So now that I canceled those two h's, I'm ready to take the limit, and because all of these terms past here are going to have some kind of h attached to them, now that I've canceled these two, I can take the limit, and that's going to go to 0. All of these terms are going to go to 0, and the final term are going to go to 0. And so I'm left with, after the limit, just n to the x to the n minus 1. And so this is just an incredibly powerful result. And this is the proof of it that I just showed you. And so now we're going to look at some examples in the next video, and I think you're going to see that these problems just take a few seconds. So see you in the next video.